purpose? The purpose is to remove those inverters on the carry path, right, to make the circuit operating faster. So this is how a circuit designer optimizes at various levels, logic level, gate level, and together sometimes, right? We implemented the transistor level and found out that the inverters are going to delay, so I'm just going back and changing the logic again. And that's the reason 270 is the prerequisite for this course. But you have to understand 270 also very well, because it's not just knowing what is sum and what is carry out. You have to understand from the very fundamental level, so that you can simultaneously apply the transistor level knowledge and the logic level knowledge to design the fastest adder. So this is one configuration, what is known as the multi-bit adder, augmented carry adder, using the mirror adder property, okay? So the mirror adder, NMOS and P-quantum, I will go through this later. It's not very important right now. I'll just go back here. For ripple carry adder, we can find out the delay is the delay through n-1 stages, the carry. So so this carry has to go through all over here, and after the carry comes over here, then the sum is generated. So the question is that whether this is generated faster or this is generated faster. That's why we take the maximum value of the carry out here, sum over here. So this is the expression for the ripple carry adder. So if I increase the number of full adders, number of stages, it linearly increases, because this is a constant term. This one basically is the reason why we don't make very long carry chain. Typically, we restrict to 4 bit of ripple carry, and then we use other ways to improve the performance. Okay, so keep this in mind. Now, since when is your CAT 4 due? Huh?
Next Friday.
Not this Friday. Ah, okay, good. So, how do you now size them? We have recognized that using 24 transistor configuration, we can make the design of the carry, the 1-bit adder, and this is the carry out without the inverter, this carry out bar actually, and this is the sum bar, this is the sum bar. We have seen that this is the expression for that, right? So how do I size them? One of the ways to size is 2, 2, 2, and this will be 4, 4, 4, 4, 4, 2, 2, and this part is 3, 3, 3, double of that, 6, 6, 6, and so on. So how many of you will be using this sizing? All of you are comfortable with that? What is the advantage of this sizing?
Symmetric rise and fall.
Pardon?
Symmetric rise and fall.
Rise and fall times are same, the noise margins, right? The following transistor sizing enables us to achieve high speed of operation as well as rise and fall delay are equal. But is it correct? Is it correct? And that's where again, as a circuit designer, you have to have a different perspective. The perspective different from the logic designer. For a logic designer, as well as the first level circuit designer, this is fine, right? The sizing of the transistors are done correctly so that the rise and fall delays are equal. What better I can do? Anybody? What better thing I can do? Any idea? I can now make a probabilistic analysis of the signal flow in the circuit, correct? If I look at this, I know that these transistors will be coming to effect only when this is 1, and this is 1, or all of them are 0, right? What is the probability of that? 1 by 8. Because there are 3 inputs. There are 8 different combinations. 1 out of 8 cases, or rather, for 1 by 8 for this and 1 by 8 for that, either this or that will be affected, right? So my point is that, am I going to give the same sizing of this as opposed to the, over here also, there are more probability that these transistors will be passing the signal than these two. So I need to now do what is called the input data pattern analysis. Using the input data pattern probabilistic analysis, I can go back and resize the transistor to further optimize my design in terms of the layout area, in terms of the circuit speed. Am I correct? Are you guys comfortable with this argument? You're okay?
I don't really understand why.
Okay, but what I said, did you hear that? What I just now told, you heard that, right?
No, I was sliding through other slides. I didn't hear exactly.
Okay. So my point is that this will be on when all these are 1. That means A is 1, A is 0, B is 0, C is 0. And this will be cut off then. So only when A is 0, B is 0, C is 0, this path will be on. Otherwise, this is not used. So why am I going to use the minimum size transistor? I mean 3. I can use less than that even, right? Because the speed is not the main factor over here. Speed is most important for these transistors because these transistors will be generating the carry. And this is some. I give less preference to this particular part of the circuit than this. But within this, these 6 transistors will be sending 6 patterns, and these 4 transistors will be responsible for 2 patterns. So I need to take that into consideration to further optimize the sizes of the transistor. Now, when I say optimization, I'm not talking about just the speed. Now I'm also talking about the power consumption, right? Because one thing we have not talked about the power consumption. The power consumption reduces if I make the transistor smaller. If I make the transistor bigger, it becomes faster, but the power consumption increases. Now I'm making a trade-off between the power consumption and speed and the input data pattern to size the transistors. And that's what it is over here. So the claim is that if I use the different data patterns and see which of the circuits in the carry path is activated, I see corresponding to 0, 0, 0, the pull-up network is on. Corresponding to 010, pull-up network is on. Corresponding to 100, pull-up network is on. In other two cases, pull-down network is on. Okay. So now, if I use this type of input analysis, I can resize the transistors, make all of them are 1, 1, 1, 1, 1, because the sum is not the bottleneck is carry. So I want to reduce the power consumption. So I make them the minimum size. And here, I actually increase the size of these because they will be passing more signals, so I need to use them faster. And I make them again the smallest size. So this is how a good circuit designer will be designing the circuit. They will be not only do the logic analysis, will do the circuit schematic analysis, then together they will do it by removing the inverters, and then they will go back and resize the transistors, looking at the data patterns, the probability of the data patterns, the probability of the signal